All right, so let's get started. I'm going to talk today on control theory. I'm going to continue with control theory for the next little while. The main focus today will be on modeling and representation of a system. And I'll tell you up front that unfortunately you're not going to understand much about this lecture. Actually, you'll understand it and you'll think you'll know. And then when you have to actually model a system, you'll realize you didn't understand anything. Okay, so I know it's going to happen, so I'm going to try to explain why, but the bottom line is that modeling a system is more art than science. You know, it's like somebody says, "Here, I'm going to teach you painting," you know, and they show you this is what each stroke looks like, and say, "Okay, now go paint the Mona Lisa." Okay, it's not going to happen. You're going to try it, it's going to not work, and you're going to try again. It's not going to work, and after 20 years, you know, eventually you get there, or maybe you don't. Okay, and that's the same thing with modeling. We often are forced to make judgment calls, and the consequences of those judgment calls are not apparent at the time that you make the call. So you say, okay, I'm going to do this, and then the consequences of that become clear only, you know, much later, and then you almost always have to go back and say, well, I better try something else, and you keep doing that until it finally works out. So I'm going to talk about that in a bit more detail. And then I'll talk about the mathematical representation. Once you have the modeling done, this is actually relatively straightforward. The modeling part is really where it gets tricky, and as I said, it's, well, let's see how we do it. Okay, so just to remind you, I'm just going to redraw the control system from before. So we have a plant, and we have the plant being influenced by two things. Oops. We have the input, we have disturbance over here, and we have some control input from a controller, and that has a control input U, the disturbance is W, the plant is G, and then you have some output which is Y, and then we have some feedback going into a measurement system, and that's usually drawn as H, and we get some feedback B, and the feedback goes into, we take the negative of the feedback and the reference R, and this gives the error E, and the controller uses the error E to decide what the what U should be, U being the control input. And so this is the kind of the basic feedback system, and these notations R, E, U, G, H, B, Y, all of these are kind of standard. So any textbook on control, they will use exactly the same terminology. And the thing that I wanted to talked about last time was this notion that we have actually got two things. One is the plant, and then we have the control system like this. And both the plant and the control system look more or less the same. In the case of the plant, we have some input, which is the input to the plant. It's got some input, control input and some disturbance input. And based on an input, the plant does something and we get some output. So that's up to us to decide what it is. And, you know, and really today it's all about how do you define what goes inside the plant? What is the plant actually doing? But at this point, what I want to mention is that if you look at the bigger orange box, that has some input, which happens to be this reference input. It has some output over there, and in the same way that, you know, the plant can be modeled, we can also model the whole system. So the outer box is called the control system, and this is the uncontrolled system. And we can now take the control system and kind of make it a little box inside a bigger box and recurse, and you can build very complicated systems this way. And in fact, that's exactly what we do. Okay, the other term that we use for this is what's called the open system, and the open meaning that there's no feedback loop, whereas this is a closed system, because we have a feedback loop. The output influences the feedback loop. Of course, you can have one closed system inside another closed system. Okay, so anytime there's a feedback loop, we call it closed, because you can kind of go back to the beginning, and it's open, you kind of flow through. I'm going to give you an example of a difference between open and closed just to give you, from the systems perspective, what this means. How many of you have studied TCP and how TCP works? TCP, flow control. Can you raise your hand a little bit higher so I can see? Okay, so about half the class. So TCP is the standard system for a protocol for the transport layer in the internet. It has something called flow control, and the flow control protocol works something like this. Basically, you control the rate at which you inject packets into the internet, and you keep increasing the rate. At some point, it's too fast. You have packet losses because you're sending too fast, and then you back off, and then you try again. So you go faster and faster, and you say, "Oops, I'm sending too fast." You go back down. And you get this kind of sawtooth pattern, and that's what TCP does. The average of this sawtooth pattern is basically going to be the available capacity on the path from the transmitter to the receiver and back. So there's some implicit or intrinsic path. Let's say you try to download a web page, your browser, there's a web page, there's some capacity on that path. That's this capacity over here. And so what's going to happen is that you're going to essentially go up and go down, go up and go down, but on average you're going to use the capacity. And the beauty of TCP is that no matter what this capacity is, even if it's very, very small or very large, eventually you will find it and you will be able to use it, and it works quite reliably most of the time. So that's TCP. This is a closed system. And the reason it's a closed system is because we are going to go down based on the feedback that a certain loss happened or some other things happened. Doesn't really matter what it is. On the other hand, imagine that you are trying to send video using a webcam connected to your computer using UDP. Now, if most of you study networking, UDP is a protocol that has no feedback. So what happens in UDP is you get your camera, you get the images, and you just basically blast them away. Daniel, you have something on your mind here? Okay. Something very interesting going on?
Yeah, we were just trying to figure out the homework.
The homework. This is not the time to do homework. The time to do homework is before. Okay. And if you want to do it, don't be so blatant about it. I remember this is a bidirectional medium. So if you can see me, I can see you. And if I call out your name, it's going to be on YouTube for the rest of your life. So your grandchildren say, "Oh, Grandpa Daniel, you didn't pay attention in class. That's why I didn't pay attention in class." Okay. So don't do it. Okay. All right. So this is a closed system, and what happens is that you're getting some feedback. With UDP, if you have a webcam connected to your computer and it's sending out data on UDP, what happens is that there is no rate. You just keep sending whatever rate there is. Even if it gets lost, it doesn't matter. Even if it gets lost, we're just going to keep blasting away at that particular rate, and consequently, it's an open system. There is no feedback. Okay. Now, one of the common mistakes that people make in any system, in any kind of research, and in particular networking research, is to take packet traces from a closed system and use it to simulate an open system. So in a closed system, for example, over here, if I were to tell you the time instance at which packets were sent, there would be whatever, there would be some particular time instance. I could say, here's a trace of packets, and I can tell you the packet times, right? Now, if I were to take this trace and say, okay, what happens if the internet had twice the capacity? Those traces are meaningless. Because with twice the capacity, it would go like this. It would not go like that. So these traces cannot be used for that. Right? But in fact, it's a common mistake that many people make, which is to take traces and say, oh yeah, I measured all the packets being sent on the link in a closed system, and then use it in a different closed system. You can't do that. If it's in the closed system, it's going to be on that closed system, and if you want to really get the intrinsic rate, you have to use the open system. So that's the difference between the two. Okay, having said that, let me move on to this notion of modeling. And so we are given a physical system. Okay, I'm going to use the example for the sake of, just because you did this in the homework, I'm going to use this the example of speed control and direction control for a car. And it's important to always keep in mind a real example. When you have complicated concepts, no matter what it is, always start with a simple example in your mind, because otherwise you get confused. So I'm going to start a simple example. So somebody comes to you and says, okay, build me a controller for speed control. Now, by the way, speed control is really pretty easy. You know, cruise control has been in cars forever. I don't know, at least 20, 30 years. Direction control, it's not there. You know, there's nothing that tells you how to do your steering wheel because it's actually very difficult. But anyway, for now, let's just look at both of these. And so with speed control, it's such a simple problem. We want to model it. Okay, suppose somebody says, model speed control for a car. So the first thing you have to do is step one is basically understand the system. Understand the system and more importantly, and its parts, its component parts. Parts and their relationship. Okay. This phrase, component parts and relationship, is super important. Okay. If you forget everything about modeling, that's the only thing you remember is component parts and relationship, you've actually got pretty like 95% of what it takes to model a system. Why is it? And the reason is because for most systems that you want to control, these are engineered systems, the behavior of the overall system can be determined by breaking it down into its components and its parts, and the component parts, and the relationships. Okay? If you look at databases, for example, they use something called the entity relationship model. This is exactly the entity relationship model. Okay? So what are we trying to do? We're saying here is some complicated thing, but I'm going to break it down into smaller pieces, and then I'm going to tell you how the small pieces relate to each other. And if I can tell you this, then I tell you how the whole thing works. And this approach is what's called methodological reductionism. Methodological reductionism. As opposed to other kinds of reductionism, which I won't go into. And this is the basis of the scientific method. Okay, this, if you remember what I told you about Newton said, okay, you know, we have this complicated thing, which is the motion in the real world. I'm going to assume there's no friction, right? And then I'm going to talk about individual things. So they're called mass. Okay, a mass is a piece of, it's mass. It's intuitively clear what a mass is, which has some motion. Motion is intuitively clear, etc. And now what I'm going to do is I'm going to talk about the relationship of the mass to motion. So the mass moves, and then there's some other mass that that interacts with it. So we're going to reduce the solar system into just masses and velocities, okay, and gravity, and that's it. So what's going on? You understand the system and say, oh, here's this beautiful solar system. If you're a painter or a philosopher, you'll say, oh, this is so nice, I'm going to try painting it. But Newton says, no, here's a mass, there's gravity, there's the distance, that's the velocity, that's the acceleration. So for Newton, everything is just masses, and so the component parts are the masses, and relationship is law of gravity. Okay, so you've taken a whole which is complex, which has relationships outside, and which has many, many dimensions. You know, there are very many different dimensions to it, but you put on your blinkers, so to speak, and you focus on one aspect of it, and you say, these are the components, this is the relationship, and that's all I care about. I'm going to ignore the rest, okay? Because otherwise it's too complicated, okay? And this actually becomes the critical part of modeling, which is what do you ignore? Okay, which aspect of it do you choose to ignore? Which aspect of it do you choose as a component part? Because if it's not in the component part and it's not in a relationship, it's not in your model. It's not there. But you don't know what it's going to be. Okay, you kind of choose what it is, you model it, then you hope everything is okay. Okay? And sometimes it is and sometimes it's not. Okay? So unfortunately, this is the place where you tend to make the most mistakes. But to illustrate this, I'm going to show you a simple model and then a more complicated model. So speed control. Okay, so let's think about it. Somebody says, build me a speed control for a car. So okay, so you say, what's the car? Well, we can view it as basically something which has an accelerator. Okay, when you press the accelerator, it has a particular speed. So we can think of it as being just an accelerator and a speedometer. And essentially, that's all we care about. The rest of the car, what are the passengers, where are they going, why are they going somewhere, we don't care. We are not authors, right? We are not novelists. We don't really care about why they're going, where they're going, what speed they want to go. Is it too slow? Is it too fast? Should they be driving the car in the first place, right? Are they legal? Do they have a license? All these things are important, but we ignore it. Right? We just completely ignore the whole thing and say, look, I'm an engineer, just tell me where's the accelerator, where's the speedometer, and don't ask me any other questions. So we look at that as a model. So then we have a very simple model. We have basically saying, if we have the input, okay, we have some plant, which is the car, and I'm going to have some accelerator setting, okay, so we have some noise, disturbance, I'm going to have some accelerator setting, and this results in the car moving. The car moves, that is the moving, and then the feedback is that I have the speedometer, okay? And I have some reference setting, so actually I should be careful. Yeah, so I have some, oops, that's not over here. I'm working backwards. Okay, so here we go. I have the accelerator setting. I guess this also illustrates the difference between a reference set point. So the reference set point is the reference speed, and the speedometer tells me what the actual speed is, okay? And the controller is going to choose the accelerator setting, right? So the reference speed is too high, the accelerator backs off, or you have a brake. Okay, I'm ignoring the brake for now, I can put the brake down, but let's assume we only have accelerator, I'm going to just ignore the brake for now, okay? But when the speedometer says too low, I press the accelerator, speedometer is too high. And you can see it's a very, very simple feedback control system, but the point is that I'm modeling all of the complexity of the car with just the accelerator, brake, and the speedometer, and that's it, okay? And that's what I mean by breaking down a complex system into its component parts. So we have to understand a system, its component parts, and relationship. Relationship is very simple. If I press the accelerator, the speed goes up. If I take the foot off the accelerator, the speed goes down. And that's all I have. Okay, let me do the other one, and then we'll take a break. And that's let's take a look at the issue of direction control. Okay, so direction control is basically we have some road. It may be a curving section of road, and it may have turns like so, and there may be other traffic, and then you have to and you may have a pull out over here, which is like a parking area that you can stop on the side, I don't know, and then you have the car, and the direction control mechanism is the steering wheel. So you kind of have to figure out, why am I doing direction control? What is it for? Okay, so one possibility, which may be the simplest possibility, is to say, okay, I'm going to tell you turn by so many, there's a turn in the road, it's going here and going here, and I want you to just change the steering wheel, and all I'm going to give you is the angle theta, and make sure the angle theta is maintained. That would be sort of the innermost plant over here. That's really straightforward. It's just the speedometer, because all I have to do is to essentially see what angle am I actually at, okay, which is the angle of the wheel, and what angle do I want to be, and if it's not the same, I'm going to adjust it, and that's really simple. But if I think about direction control as being more complicated, which is I want to allow the car to make the turn automatically. I just want to sit there reading the newspaper or reading a book, and the car is going to turn itself, okay? The system and its component parts are very complicated, right? For example, I might have to turn the steering wheel in advance. I may need to go left and then right, because there's a turn that I will need to make like that, right? I need enough clearance. If it's a big truck, for example, I may need to actually combine the control of the speed and the direction at the same time, because I'm going to stop the car, because there's a red light over here, or a stop sign, and then I'm going to turn the wheel. Okay, or there may be cars ahead of me, so I need to overtake them, stop. So there's many, many reasons why I may want to change the angle of the car. Okay, if you start including those components, Okay, this direction control problem, okay, if you view that as basically what angle do I keep the steering wheel, is extremely complicated. Okay, it's extremely complicated. It takes into account so many different things. So what should you take into account? You know, should you say, well, I'll do direction control, but only on a freeway which has no other cars, and you know, where all I'm doing is staying between these two dotted lines? Or are you going to say, well, I'm going to direction control, but I'm going to do it only for parallel parking. So there are some cars where you can say, press a button and it will actually park the car for you. I believe some high-end luxury cars do that. So then it's a very limited problem scenario, right? I have a particular space, I have a car, I'm going to just back into it, and that's a very easy direction control problem. But the general direction control problem is very, very complicated. And so you kind of have to step back and choose a particular thing. So when the car designer said, I'm going to do parallel parking as a direction control, steering wheel control, they took a very small problem. They said, look, we can't solve the general problem. We're going to reduce the scope just to one single thing, and this one single thing is parallel parking. There it's very simple, and we have a particular amount of space. I know the car is going to fit in or not. I press the button, it's going to do the rest, and that's great. But the general problem, you have to figure out what are the component parts. And in this case, the component parts include the visual system to determine what's happening around you. And that's what makes it very, very difficult. And then the relationship between the component parts, the exterior symbols, and the relationship to the actual inside system. So going back to this with the direction control, we have some reference, you know, which says, you know, some high order thing that we want to accomplish, and then the controller has got, in addition to these inputs, I guess it also has some inputs from the visual side. You know, it says what does it see? It uses that to accomplish those particular goals. Okay, I want to say one thing before we stop, which is that when we look at this plant over here, what is the input to this plant? The actual input to this plant is basically U plus W. Okay, what it's getting is the U plus W. So when we consider the plant, we can consider modeling it either as only on the U or on U plus W. So we have to be fairly explicit about, are we modeling just the input, or does the input include the disturbance as well? And it turns out that based on how you do it, the plant model changes, obviously, because we have different inputs coming in. So when we'll do an example of that, it will become clear. But at any rate, this is sort of the hard part, the understanding the system parts, the parts of the system, the relationship. And once we understand this, we can kind of move on to the remaining steps, which are, as I said, a bit easier to figure out. Okay, are there any questions about this? Yeah.
Sort of. One place in one and another place in the other.
Right. So I guess I can rephrase the question as, why is speed control not as complicated as direction control? Right?
Right.
And the answer is yes, it is. Because obviously if I have traffic lights and stop signs and so on, but I wanted to do one simple and one complicated one. Right? If they're both complicated, it's not so easy. I want to show you the difference between the two. Right. So it's a purely educational tool. It's not reality.
Sorry, I didn't mean to pull back the curtain.
No, that's okay. No, in reality, even speed control of the sort that you're talking about is complicated. But cruise control, where you're sort of an open road and all you have a set point for speed, that is relatively easy. In fact, it is easy. So that's why every car has it. Even the cheapest car has it today because it's pretty straightforward. Yeah. And add now some more terms, which is effort, flow, power, energy, active. So in doing the modeling, it's useful to keep in mind these 6 terms: effort, flow, power, energy, active, and passive. And these are, you can think of them as sort of hints, in where to look. Okay, based on experience, there is some kind of understanding of, if you look at these concepts, they'll be useful. So I'll tell you what they are. The first one is effort. So effort, intuitively speaking, is how much effort you're putting into the system. Okay, some kind of power. It's not power, but like if you have a bicycle pump, your effort, your manual effort. Okay, that's the effort you're pushing into the system. And mechanical systems, or most systems actually, can be viewed as redistributing this effort over the remaining part of the system. So the effort is concentrated at some point, and somehow this This effort is being redistributed, and the way it's being redistributed is the flow. So in the case of a bicycle pump, my effort results in the flow of air through the pump. In the case of the car control, the effort is sort of the amount of actually the amount of local thrust from the engine, but that's coming controlled by the accelerator. So my effort can be viewed as the accelerator. The accelerator is the effort, and the flow is the movement of the car. Okay. If you look at computer networks, we don't actually have any effort per se, but in some sense, the amount of data that you have to send represents the amount of effort that you have, right? So if you have to send a small file, it doesn't require much effort. But if you have a few gigabytes to send, it's more effort. If you have a terabyte of data to send, it's a lot of effort, right? And so the amount of unsent data to me seems to be the best way to think of effort. And in the case of a computer network, flow is sort of the movement of the packets over the internet, over the communication link. That's your flow. So whenever you model a system, so if you looked at TCP, what was going on, we have this behavior of flow. That rate is a flow, and that's because you have stuff to send. So you have your effort, that's all your data to send, and then the flow is the actual rate at which the data gets sent. So when looking at a system model, it's often useful to ask yourself the question, where is the effort coming from and what is the associated flow? Okay, and the answers will differ. In an electrical network, effort is the amount of electromotive power which comes from a battery in a DC system. Okay, so if you have a cell phone, the effort at some basically is coming from the battery inside, and the flow is all the flow of electrons through all the circuits. Okay, so that's one particular model of a cell phone. Obviously, there are other components as well. So that's effort and flow. In the homework question, I think I asked what are the effort and flow variables for a controller for speed control. So the effort variable in this case, I would say, is the accelerator, right? Because the more the accelerator, the more effort there is, and the flow variable is the movement of the car itself. Okay, that's the flow. Okay, it's not the speedometer, which is a measurement of the flow, but the car movement itself is the flow. Yeah.
Can we consider the fuel imparted to the engine as effort?
Yeah, you could say that, but the amount of fuel. I mean, yeah, that's right. That's what the accelerator controls. Yeah, that's it. Okay, so the product of effort and flow is called power. Okay, by definition, effort times flow is power, where effort is measured in some way, flow is measured in some way. So in the case of an electrical system, which is pretty straightforward, the effort is voltage, flow is the current I, and the power is V times I. Okay, and that's in the mechanical system. We can analogously define mechanical power and hydraulic system and so on. So in the kinds of mechanical systems that we study, in a computer system, we can define effort and flow, but the notion of power is not used very much. Energy is basically power times time, the time over which the power is expended, or to be more precise, the integral of power times dt is going to be the energy. Okay, so if I have particular, if you take electrical energy, you have, let's say, 5 watt element of something that consumes 5 watts, like a I don't know what would take 5 watts. A night light takes about 5 to 15 watts, or a LED takes about 5 watts, and you have it for 1 hour, that's 5 watt hours, that's energy. So watt hours is energy, watts is power. Okay, so power is sort of how much effort multiplied by the velocity. The more the effort, the more the velocity, the more the power. And then, yeah, Tanya.
What's energy in a network setting?
In network setting, it would be, if I wanted to do it this way, so effort in a network setting would be in bytes. Okay, let's say megabytes to be more realistic. Flow would be in bytes per second. So power would be in megabyte, okay, or megabyte square per second. Or maybe I should do flow in megabytes per second just to be consistent. Okay, or bytes square per second. Energy would be the integral of that. So it would be in megabytes square. Okay, so it's a square of the megabytes unit. So that's network energy in megabytes square. It looks weird, but then the first time you saw the definition of acceleration was what? G is 9.8 meters per second, that looked weird too. It's not that weird when you think about it. Okay. To be more precise, basically, let's just say that this is time, and this is the bit rate. Okay, let's say bits per second, or megabits per second, or whatever. The area under the curve is sort of the amount of data transfer. So that's in megabytes, right? Data under the curve is in megabytes, obviously. That's how much data got transferred. And then that was corresponding to some effort, which was, I had 100 megabytes to transfer, for example, and I transferred the 100 megabytes over some period of time. So the energy would be in megabytes square rather than megabytes. Okay, effort would be in megabytes, and the energy would be in megabytes square. So if you're a large file to transfer, the amount of energy is quadratically growing with the file size, not linearly growing with the file size. Okay, that's an intuition you can get, which actually, now that I think about it, no networking textbook or no networking researcher has talked about, since I happen to know something about it. So that's a nice insight. The energy of your transfer is quadratic, not linear. So, but what does it mean? I don't know. It sounds pretty cool though. I have quadratic energy. Okay. But does that answer your question? Yeah. Okay. Any other question? I have to write a paper about this now, but I can't remember. I don't know what to say about it. Okay. But it's worth thinking about anyway. What's the energy of a file? It's quadratic. Okay. What's the energy of spam? It's quadratic in the amount of spam that's sent. It's also interesting to think about. Okay. Active and passive. So active elements are, they generate power. And passive elements basically store energy, not power, energy. So the simplest way to understand it is to think about electrical system where an active element, like a battery, is going to generate power. It's generating power, or a generator or something like that. Where a passive element is like a capacitor. It's just, it's not doing anything. It's just storing energy. Or of course, a battery that's storing and discharging is essentially nothing more than a capacitor. That's also passive. If you think of a mechanical system, a spring is a passive element. When you compress it, it stores energy, and when it releases it, it releases energy. Or if you take a guitar and you pluck a string, the active part is the plucking of the string, and then the passive part is the string. The string itself stores energy, and that's why it vibrates. So the vibration of the string is in fact a passive energy. So again, these are all hints. These are not like, oh, you must find the active and passive elements. But it's convenient, it's useful to say, okay, what are the active elements, what are the passive elements, and to think about it. Okay, so the active elements are basically generating the power and the effort, and the passive elements are the redistribution of the power throughout the system. Okay, so that was step one, just to kind of understand what are the parts, what are the active, passive parts, what's energy, what's flow, and so on. Step two is the relatively easy part, which is once you've got the components, what you want to do is to essentially find the laws that govern the behavior. Okay. So, for example, if you take a particular electrical network, you'll say, okay, it obeys Ohm's law. If you have a mechanical network, it obeys Newton's laws of motion. If you have a computer network, then you can say, okay, I'm going to have a capacity on a particular link which cannot exceed certain number of bits per second. So I know that the bits per second, that is the flow, cannot exceed certain amount, right? If I have a buffer of particular size, the law says that when the buffer size is exceeded, packets are dropped. So I have a law. Okay. So these laws or rules of operation are basically tell us the constraints under which the system operates, and also it tells us the relationships, okay, the mathematical relationships that we have. So for example, one of the laws of the car is if you press the accelerator, the car accelerates, goes faster, right? So that's the rules of operation, and there's a law, and the law says presumably that if this is the accelerator pedal, and this is the distance between the accelerator pedal and the floor, and that's x, and let's say we start 0 over here, and this is going to be some value m. So we just say the law says that 0 is less than x less than equal to m, and then v is equal to some function of x, where v is the velocity. And if you're lucky, F is linear. Now we can assume it to be linear anyway. Let's hope. Okay, if it's not linear, I'll tell you what to do in a minute, but we can assume F is linear. Okay, so now we have a